Now that we've reviewed some of the basic concepts of functions in general, we're going to walk through and talk about some special types of functions that we're going to encounter again and again. And now the first type we're going to talk about is polynomial functions and rational functions. But let's start with the simplest possible function, and that's a constant function. So a constant function outputs exactly one real number for every input. So our function f of x will just be some number c, where c is a real number. And even though these are the simplest types of functions, they can be really confusing. Because let's say I ask, what is f of 2? Well, you say, okay, I'm supposed to, everywhere I see an x, plug in 2. But there are no x's. I only have that the function is equal to the constant. But that's because for every input, in this case 2, I output the same number c. If I wanted f of 0, I would get c, whatever that real number is. So note that the domain of a constant function well, I can plug in any real number and get the same constant output. So the domain is all real numbers. And now the range of the constant function, the set of outputs where there's only one output. So the range of a constant function is just the one number, c. And we can write that just as the set containing the number c. There's only one output. For any input, which the input can be any real number, we have exactly one output, c, no matter what I plug in. So if I plug in -1, I get c. If I plug in 100, I'm going to get c. So it's very, very simple, but it can be a little tricky because, again, there are no x's to plug numbers into, but that's because every output will always just be c. So stepping up just a little bit is another type of function that I'm sure you've seen over and over again, and that's a linear function. So a linear function, as the name suggests, is just a line. The graph of a linear function is a line. But a linear function has the following form. F of x is equal to mx plus b, where here m is a real number called the slope, and then b is also just a fixed real number called the y-intercept. And I'm assuming this is a review for a lot of you. The slope is just kind of the rise over the run, because the graph of this function, if we look at the graph, so it's going to look something like this. So the slope is just how much I rise when I go over 1 unit, like that. And then the y-intercept is where I cross the y-axis. So that's where these names are coming from. And like I said, the graph of a function, of a linear function, is just a line. And now, as long as m is not 0, so the slope is not 0, the function f is 1-to-1, and the inverse, well, we can just solve. we do our same tricks. We solve for y, or we switch x and y and solve for y in terms of x, and the inverse ends up just being x minus b over m. And here we see definitely m needs to be not 0 because we're dividing by 0 here. So that is as long as m is not equal to 0. The function, our linear function, will be 1 to 1. So there will be a unique output for every input. And then the inverse of a linear function is again a linear function, and it looks like this. So moving on from linear functions, we'll jump up and talk about power functions. So a power function, well, it's called a power function because it really is just a power of x. So it looks something like this. F of x is equal to c x to the a. And here, c and a are both real numbers, and we're going to require that c is not equal to 0. Because if c is equal to 0, this is actually just a constant function. It's just the constant function equal to 0. So a special case of a power function occurs when this a is actually a non-negative integer. And this is the case we're going to look at a little bit more. So special cases when a is a non-negative, so I'm including 0, non-negative integer. Okay, so like x squared is a power function, or 3x cubed is another power function. And so in this special case, what we want to note is that f is 1 to 1 if n is odd, if a is odd. Now notice that makes sense because I'm assuming that, okay, in general, a could be like a half or square root of 2 or whatever, but in the special case when a is a non-negative integer, if a is odd, an odd non-negative integer, so 1, 3, 5, 7, whatever, f is 1 to 1. And then f is not 1 to 1 if a is even. But in both cases, the domain of f is all real numbers. There's no problem plugging in any real number into a power function. And now the range is a little bit trickier. So the range will be all real numbers if a is odd. And then if a is even, it's either going to be 0 to infinity or negative infinity to 0, depending on whether c is plus or minus. But we'll explore that a little bit later when we look into actually the calculus of power functions. That's when that will come up again. But next, we want to talk again in this special case of power functions about what's called the end behavior of the power functions. Okay, so notice that I have this nice table here, and I want to pick up just a couple of things that we're assuming. So we're assuming that we have a power function, c x to the n. Now I'm using n here because I only want to consider the case where n is actually a natural number. So that would be a non-negative integer not including 0. So 1, 2, 3, 4, 5, etc. And what we see is that we have 4 cases. And the cases are based on whether or not n is an odd or an even number, and whether the number that we're multiplying the power function by, which we're assuming is not 0, is either positive or negative. And we're looking at what's called the end behavior. And the easiest way to understand the end behavior is to actually look at a graph. So I want to just do a quick sketch of these four cases of power functions, because this is going to be very important later when we look at what's called limits at infinity of different types of functions. So I'm just going to sketch a quick graph of each of the cases, and I'm sure you've seen a lot of these before, but let's just sketch them again. So in the first case, this is an odd power function, meaning that the power is odd, and c is positive. And now what this is saying is that the end behavior, as x goes to positive infinity, so this way, the function f is also going to positive infinity, like this. And then as x goes to minus infinity, the function is actually dropping off to negative infinity, like that. That's if c is positive. If c is negative, the graph is actually reflected over the x-axis, like this. So the end behavior is opposite. As x goes to minus infinity, f goes to positive infinity. And as x goes to positive infinity, f goes to minus infinity. Now the cases for n being even are a little bit different. So if c is positive, this is like our classic parabola. So it's a happy face because it's positive. The coefficient c is positive. So as x goes to plus infinity, f goes to plus infinity, and as x goes to minus infinity, f goes to minus infinity. And then if we take c to be negative, the graph gets reflected over the x-axis. So we have a sad face, like this, because our coefficient c is negative. Okay, and again, as x goes to minus infinity, f is going to minus infinity, and as x goes to plus infinity, f is also going to minus infinity. So this is the end behavior of these power functions, and that's going to play an important role later on in the course. So now that we have a handle on power functions, we can define polynomials. And polynomials are kind of the bread and butter of what we're going to be doing. Now we're going to consider more complicated functions as well, but a lot of the ideas will be best understood just by looking at polynomials. So let's go ahead and define what we mean by a polynomial. So a polynomial function, and polynomial, what this word actually means, poly meaning many, nomial meaning term, so it's a many term function. So a polynomial function all it is, it's a sum of power functions c x to the n, where here we're assuming that n is a non-negative number, non-negative integer. So now I say non-negative because I actually want to include 0. Because notice that if n is equal to 0, x to the 0 will be 1, and we'll just have c. So we're actually allowing constant terms. We're allowing x to the first terms, x to the second terms, x to the third terms, etc. So that's what a polynomial function is. And so a general example of a polynomial function is something like this. So it might look like 2x cubed minus 4x plus 1. That's an example of a polynomial function. Now there's a couple important things that we need to identify about a polynomial function. So the degree of a polynomial function is the largest power n. So in our example, let's identify the degree. So the degree is supposed to be the largest power of one of the terms, and notice that here that example is 3. So this example is a degree 3. And now the leading term is the actual power function. With the largest n. Okay, so let's identify that in our example. So the leading term is going to be this entire power function 2x cubed. That's the leading term. And then finally, we have what's called the leading coefficient. And the leading coefficient is going to be the number that's multiplying the highest power of x in the leading term. So in this case, the leading coefficient is going to be 2. And the leading coefficient is going to play a big role in the end behavior of the polynomial. But we're going to talk about that a little bit later. So just a couple of notes about polynomials. Polynomials are not, in general, one-to-one. So most polynomials don't have inverses. And then the next note is that polynomials have all real numbers as their domain. So there's no problem plugging any real number into a polynomial and outputting a real number. So that is just a couple of the key facts about polynomials. We'll see these time and time again. I will make a note that a linear function is an example of a polynomial function. Notice that a linear function is a degree 1 polynomial. So let's talk about a few other features of polynomials. So we already mentioned that a linear function is a degree 1 polynomial. So a degree 2 polynomial also has a special name. It's called a quadratic function. And we can actually keep going. If you're really up to date with your Latin, this is actually not too hard. So a degree 3 polynomial, well, quad, okay, so then we have a cubic function. And then we'll just say, etc. We have a quartic, quintic, so degree 4 would be a quartic, quintic would be a degree 5, you could just keep going, on and on and on. So those are just some special types of functions that you'll see thrown out. This is a quadratic function, this is a cubic function, but they're all just types of polynomials. They're all just sums of power functions where the powers are non-negative integers. So this next point is actually something true about all functions in general, but it's discussed a lot with polynomials. So the zeros of a function are real numbers in the domain of the function. So let's say our function is f. So the zeros of a function f are real numbers in the domain of f, such that, well, the word 0 kind of gives it away. F of x is equal to 0. So we're looking for numbers x in the domain of the function for which f is equal to 0. And now these real numbers that we're just calling x, so the real numbers x in the domain of f such that f of x is 0, are actually what are called the zeros. So the numbers x that you plug into the function to get 0 are called the zeros of the function. It's a little confusing, but you'll get the hang of it. Okay, so for a degree 1 polynomial, finding the zeros is really easy. Because remember that a degree 1 polynomial looks like this. Okay, and so again, we need to assume that the slope is not 0. So if the slope is not 0, then there is exactly 1 0. And it's given by, well, you just set this equal to 0 and solve for x. Okay, so it's going to be negative b over m. That's going to be the 0 of the degree 1 polynomial, the linear function. Okay, so you just plug in negative b over m, you're going to get 0 for the function, assuming that m is not equal to 0. So for a degree 2 polynomial, this is a really good review. So it's kind of fun to go up to people on the street and ask them to remember the quadratic formula. And a lot of people may or may not remember it, but it's even more fun to ask people, what is the quadratic formula used for? Well, the quadratic formula is used to find the zeros of a degree 2 polynomial. So remember, this is again called a quadratic. And a quadratic has the following general form: ax squared plus bx plus c. Okay, and again, we're going to assume that a is not 0. Otherwise, it's actually not a quadratic. If a is 0, then it's really just a linear function. So if a is not 0, the zeros are, so it's negative b, so it's negative the coefficient in front of the x to the first term, plus or minus square root of b squared minus 4 times a, so times the leading coefficient, times c, where c is the constant term, all divided by 2a. So you see, of course, we need a to not be 0, otherwise this doesn't make sense. Just like here, we needed m to not be 0. And now you say, okay, well, this plus or minus just means that for one of the zeros, there's actually possibly going to be 2 zeros. One of them I'll take the positive square root here, and one of them I'll take the negative. But there may actually be no zeros. So notice that it could be possible for there to be a negative under this square root. Or this square root, underneath the square root, could be exactly 0. So there's actually 3 possible cases. So a quadratic could have 0, 1, or 2 zeros. And what we see, how could we have 0 zeros? Well, that's if this factor b squared minus 4ac is negative. We have exactly 1 0 if this factor b squared minus 4az is actually equal to 0. And then we have 2 zeros if this factor b squared minus 4ac is greater than 0. And so because of the importance of this term underneath the square root, it actually gets a special name. So it's called the discriminant. It's the discriminant of the polynomial. Now there's also some special cases that can occur with quadratic functions. So quadratic functions, actually in general polynomial functions, can be factored. And this is oftentimes a better way to find the zeros. And the quadratic formula is always going to work, but in some cases we can factor the quadratic. So if the quadratic looks like this, ax squared plus bx plus c, what we're looking for is we're actually looking for numbers that I'll call alpha, beta, gamma, and delta. So these are numbers that when I FOIL out, so I multiply this term by this term, I use the distributive property, this term times this term, etc. So if I FOIL this out, so first, outside, inside, last, I should get exactly this. So if I'm lucky and I can actually guess what these numbers are, now that's not always easy, but what we're looking for alpha and gamma to multiply together to give us A. We're looking for beta and delta to multiply together to give us C. And we're looking for alpha times delta plus beta times gamma to equal B. So if we can sort of guess from these conditions what these numbers are, then we can actually factor the quadratic. And so why does this help us give the zeros? Because if I set this equal to 0, there's this really important property of the real numbers that if I'm multiplying two things together and that product happens to be 0, then one of these two factors has to be 0. So either alpha x plus beta is 0, or, there's that keyword or again, gamma x plus delta is 0. But that means that either x is equal to negative beta over alpha, or x is equal to negative delta over gamma. And what you see is that these are actually exactly the zeros you will find in the quadratic formula. So if we can factor, and I'll do an example in a second, then we can very quickly find the zeros of a quadratic, and in general for higher degree polynomials. So let's do a quick example just to illustrate what I mean in case you forgot. Suppose that we had x squared minus 5x plus 6. Okay, and I want this to equal 0. So here's my quadratic function. I'm setting it equal to 0 to find the zeros of the function. Now notice that my a here is 1. So that tells me that alpha times gamma has to be 1. Okay, well then I'll just let alpha and gamma equal 1. So this should be x plus or minus something, and then x plus or minus something. Now c is equal to 6. So that means beta times delta, these two numbers that I'm adding, should multiply together to give me 6. And then also, well, since, again, alpha and gamma are 1, delta plus beta should be negative 5. So I'm looking for two numbers that multiply together to give me 6 and add together to give me negative 5. Well, that's negative 2 and negative 3. And now again, by the zero product property, either x minus 2 has to be 0 or x minus 3 has to be 0. Okay, so then x equals 2 or x equals 3. Those are the two zeros of this quadratic function. So we talked a lot about how to factor a quadratic function or a quadratic equation. But I mentioned that for higher degree polynomials, it's also very useful to be able to factor them. And so I included just a list of very common factoring techniques here that you may need to use sometime later in the course. And we definitely will use these later in the course. So I would suggest maybe just keeping this as a reference. So when you see something like a difference of cubes, x squared minus a squared, where a is a real number, know that it factors as x minus a times x plus a. When you see x cubed minus a cubed, know that it factors as x minus a times x squared plus ax plus a squared. Now this next one is just kind of a general phenomenon of the difference of squares, difference of cubes. But it's also useful to know how squaring x plus a expands and how x plus a cubed expands. So it's just something to keep in the back of your mind. So when you see something like x cubed minus 8, you should think right away, oh great, I can write that as x minus 2 times x squared plus 2x plus 4. Because 8 is 2 cubed. So it's going to be really nice if you can remember, okay, maybe you're taking a limit, derivative, something. We'll see this later. You may see something like this. Well, being able to factor this is going to allow you to work through the problem a lot easier. So the last thing we're going to talk about in this topic is what's called a rational function. Now we're not going to say much about rational functions right now because really we're going to discuss them once we start talking about limits and in behavior of functions actually in the course material for calculus. But let's just introduce what a rational function is. So a rational function, and now it's sort of like a rational number. So remember, a rational number is a quotient of two integers. A rational function is a quotient of two polynomials. Let's say p of x and q of x. So our function looks something like this. P of x divided by q of x. So we have a polynomial in top with some degree. We have a polynomial in bottom with some degree. And I'm sure you can remember from your pre-calculus class that you learned a little bit about rational functions and really some useful facts regarding the degree of the numerator, the degree of the denominator. We're actually going to go in and prove some of those facts that you may remember from pre-calculus. But for now, just know that a rational function is the quotient of two polynomials. And now the domain of f, well, it's just going to be the set of real numbers. Remember that the domain of a polynomial function is all real numbers, so there's no problem unless, so we need to think about the zeros of q, because a zero of q is going to make the denominator 0, and we're going to be dividing by 0 which is a problem. So the domain of f is going to be all real numbers, except for those that make the denominator 0. So x and r such that q of x is not equal to 0. That'll be the domain of a rational function. In general, rational functions will not be one-to-one. Sometimes they will be, but in general not. So in general, they will not have inverses. And like I said, we'll talk a little bit more about the end behavior and finding the zeros. We'll actually spend some time thinking about how to graph rational functions actually in the calculus course. Okay, so for this polynomial, we want to do the following. State the degree, describe the end behavior, and find all the zeros, if there are any. So, what is the degree of this polynomial? Well, it's degree 2. Because if I look at the highest power of x, look at the power, it's 2. Now the end behavior, this is an even degree polynomial. So if we remember from our chart, the leading coefficient is positive, which means that I can ignore the lower order terms. So if I just sketch what it looks like, well, I actually can just sketch what this function is. It's a parabola, but specifically because it's even, the degree is even, and the leading coefficient is positive, x is going to, as x goes to infinity, f is going to infinity, and as x goes to minus infinity, f is also going to infinity. So there's the end behavior. Now to find the zeros, we want to just use the quadratic formula. But remember, what does the quadratic formula say? It says negative b plus or minus square root of b squared minus 4ac over 2a. And we looked at this discriminant. And we said, okay, if this discriminant was negative, there are no zeros. If it's 0, there's 1 0. And if it's positive, there are 2 zeros. But look at the discriminant here. First of all, let's note what a, b, and c are. So a is the coefficient of x squared, so a is 1. B is the coefficient of just x to the first, which is 0. And then c is the constant term, which is 1. So b squared minus 4ac is actually negative 4, which is less than 0. So there are no zeros for our function because the discriminant is negative. And we can actually see from the graph, I drew this accurately, this should pass through positive 1 here, that the function never hits the x-axis. The zeros are the points where the graph hits the x-axis. Well, there aren't any, so there are no zeros for this function. Okay, so again, this is a degree 2 polynomial. So it's a quadratic, in other words, degree 2. Because I look and the highest power of x is 2. Okay, so the end behavior, this is again a quadratic. It's an even degree polynomial. So it's either going to be a smiley face or a frowning face, some sort of parabola. But because the leading coefficient here is negative, I know it's going to be inverted, like that. So as x goes to infinity, f is going to be going to minus infinity, and as x goes to negative infinity, f is also going to be going to negative infinity. Okay, so to find the zeros, I could use the quadratic formula, but I actually want to notice negative 2x squared minus 7x minus 4. I'm looking for the x values that give me 0. I'm going to notice that this will actually factor. And so how do I know it factors? Well, it's just a little bit of practice. The more you see quadratics, the more you start to realize when they're going to factor and when they're not. And in this case, I've noticed that it factors. Now it's okay if you don't notice that it factors, because you can always just use the quadratic formula. That will always work. But if you can see how it factors, it makes the problem a lot easier. And so I'll leave it to you to verify that if I FOIL this out, I'm going to get exactly what I start with. But now I know that either negative 2x plus 1 is 0, using the zero product property. It's a tongueful. So the product of these two things have to be 0, so one of them has to be 0. So that's what I'm writing here. So either x is 1/2 or x is 4. And I got 1/2 by just adding or subtracting 1 and then dividing by negative 2. So here are our two zeros, 1/2 and 4. Okay, so this guy is a little bit more interesting. This is a degree 4 polynomial, so a quartic. And again, I see that by noticing that the highest power of x is 4. This is again an even degree polynomial. So it's either going to be going to infinity as x goes to plus or minus infinity, or minus infinity. And because the leading coefficient is positive, I know my function is going to look something like this. Now, it's not necessarily just going to be a parabola, but it's going to be coming down this way and then maybe doing some stuff and then going that way. Okay, so I don't really know what's going on kind of in the middle, but I know as x goes to minus infinity, the function is approaching infinity, as is the case when x is going to plus infinity. The function is approaching infinity. Okay, and we'll actually learn how to draw what this function actually looks like with more detail using some of the tools we'll develop in calculus, which is really cool. But for now, we just know the end behavior. We just know it's coming in from infinity and then going off to infinity to the right. All right, so to find the zeros, now this is not a quadratic. We talked a lot about quadratics. So how do I find a 0 here? Well, the reality is I really just need to guess. Okay, I know that sounds a little, shot in the dark, but sometimes you just have to guess. And now there are ways to figure that out. If you remember, there's something called the rational root theorem, and that's actually what I'm going to use here to make an educated guess. I know that if there's a rational root of this function, then if I look at this, okay, the leading coefficient is 1, the constant term is negative 2. My options are basically divisors of 2. And just looking at this, I'm going to check negative 2. So notice that if I just plug in negative 2, what am I going to get? I'm going to get 16 minus 16 plus 2 minus 2, which is 0. Okay? So I know that negative 2 is a 0. So how does that help me? Well, there's also something called the root factors theorem that tells me if I can find a 0, then I can actually factor the function. I can write f of x as x plus 2. Okay, so basically a factor that if I plug in negative 2 gives me 0, a linear factor, times some other polynomial. And what I need to do is actually figure out what this other polynomial is. And this other polynomial is going to be the quotient when I divide f by x plus 2. Okay, so what do I mean by that? I need to do some long division. I'm literally just going to divide x plus 2 into x to the 4th plus 2x cubed I'm going to put plus 0x squared, kind of like when you do division and you have 101, you leave a 0 for the 10 spot. And then minus 1x minus 2. Okay, so how does this work? Well, x plus 2 goes into x to the 4th, x cubed times. And so then I can multiply this out. I have x to the 4th plus 2x cubed, and then nothing else, and then I'll subtract. So I'll just get 0. But then I need to bring down the 0x squared, the minus x, the minus 2, so I just have minus x minus 2. And x plus 2 goes into negative x minus 2 minus 1 times. So then I multiply and I get minus x minus 2, and I get 0. Okay, so my remainder is 0, and my quotient is x cubed minus 1. So what I've done is I've factored my polynomial as x plus 2 times x cubed minus 1. And you can verify that if you multiply, FOIL this out, you'll get back what you started. But look at this x cubed minus 1. This is a difference of cubes. And what I mean by that is it's x cubed minus 1 cubed. So it actually factors as x minus 1 times x squared plus x plus 1. Okay, so now I'm really making some real progress. I have 2 linear factors and then this quadratic factor. And actually the quadratic factor, if I look at b squared minus 4ac, the discriminant, it's going to be negative, it's going to be 1, so b squared is 1, minus 4, so that's negative 3, which is less than 0. So that means this quadratic factor has no zeros. So if I set this equal to 0, so if I set f of x equal to 0, this factor is never 0, so one of these two factors has to be 0. So x plus 2 equals 0, or x minus 1 equals 0. So then I have two zeros to this function, x equals negative 2, and x equals 1. And those will be the only zeros of this quartic polynomial.